These are simple problems involving calculations of pressure. Pressure is force over area, where force is typically in newtons and the area can be in square centimeters or square meters. The unit of pressure is a combination of your unit of force divided by your unit for area. For problem 32, we're asked to calculate the pressure that a 10 Newton block exerts on the table it rests on if its area of contact is 50 cm squared. So we use our equation. Pressure is force over area. Divide 10 newtons of force by an area of 50 centimeters squared to end up with this value, zero point 0.2 newtons per cm squared. However, if we want to use another more commonly used unit, we can do this conversion. 50 centimeters squared for area can also be written as 50 cm times cm because cm times cm is cm squared. And if we want to change this to another unit, say meters squared, we would have to apply a conversion factor twice. Conversion factor relates your desired unit with your given unit. So every 1 meter is 100 cm. Express that as a fraction, it is a conversion factor. If you use one conversion factor, you're able to get rid or cancel out just one unit of cm. So you do it twice. And when you do that, 2 units of centimeters will cancel out, and you're left with meters times meter, which is meter squared. When you perform your calculations, 50 times 1 over 100 times 1 over 100, you end up with 0.005, and then meters times meter is meters squared. Now you're able to convert or change your value of 50 cm squared to 0.005 meters squared. If we go back to the original calculation where pressure is force over area 10 newtons over 50 cm squared, we can replace 50 cm squared with 0.005 meters squared. And doing that will give us a pressure value of 2000 newton per meter squared. Now, the reason why we did this is because every 1 newton per square meter is the same as 1 Pascal. So we can say that the pressure for this problem is either zero point 0.2 newtons per cm squared, or it can also be 2000 pascals. Either one is correct. Pressure exerted by liquid is the product of weight density and depth. Weight density is a constant which depends on the fluid. So if it is water, we're going to use 10,000 newtons per cubic meters. For all of these problems, we're going to disregard the pressure due to the atmosphere above. So for problem 33, you have a 1 meter tall barrel and it's filled with water. We're asked to show that the pressure at the bottom is 10,000 Newton per square meters, which is also 10 kilopascals. So apply the formula, multiply a weight density constant of 10,000 Newton per cubic meters by our depth of 1 meters, and we end up with this 10,000 Newton per square meters, which can also be rewritten as 10,000 pascals. For problem 34, we're asked to show that the water pressure at the bottom of the 50-meter high water tower in the chapter opening photo is 500,000 newtons per square meters, which is also approximately 500 kilopascals. We use the same formula. It's still water, so we use 10,000 Newton per cubic meters for weight density, but this time our depth is 50 meters. So from 1 meters to 50 meters, and you'll notice that your pressure at the bottom is 50 times as much. So you have 500,000 Newton per square meters, which is also 500,000 pascals, which is also 500 kilopascals. For problem 35, the depth of water behind the Hoover Dam is 220 meters. We're asked to show that the water pressure at the base of this dam is 2,200 kilopascals. So we use the same formula, weight density multiplied by depth. So here is the same weight density as before because the fluid is still water, 10,000 newtons per cubic meters. And this time our depth is 220 meters. So you'll notice here it's the highest depth in these three sets of problems. So it should make sense that it will be the highest pressure at the bottom. So you have 2,200,000 Newton per square meters, which is also this value, 2,200,000 pascals, which is also 2,200 kilopascals. Either of those units will do. I'd like you to notice that in all of these problems, there is a direct relationship between the depth of your fluid and the pressure at the bottom of that fluid. The deeper you go, the greater the liquid pressure.